Hiya, so today we're going to be having a look at implicit differentiation. This is a type of differentiation that we use when we've got equations similar to this one here. So if you look a little bit more closely at this equation, you've got x's in there, which is fine, but we've also got y's, and not just a y on its own, but a y cubed, and then a y in a separate term, and it's going to make it very difficult for us to have a function in terms of y is equal to sort of something x cubed plus something x squared perhaps. We're not going to be able to do that in this situation. Rather than having a large amount of algebra to sort of work through to try and put this in terms of y, what we can do instead, if we need to differentiate it, is use this idea of implicit differentiation. So let's get started. So we're ready to differentiate all of this. We know that the question is asking us to find dy by dx, so I'm differentiating their term to term with respect to x. So to get started, it's difficult because you're used to sort of putting an equals there, but in this case we're going to try and avoid doing that because of the way that the question's set up. So differentiating my x cubed term, that will give me 3x squared. Differentiating x, that will change to just positive 1. Now the next part, differentiating y. I can differentiate the y because I know the process of differentiation, so that would be 3y squared. However, initially I was asked to differentiate with respect to x. Because I've differentiated a y, that means I'm going to have a little bit left over, and that little bit left over is going to come in terms of dy by dx. So we're going to leave that there purely because we're differentiating a y term when we were asked to differentiate with respect to x. So continuing, if I have a look at my next term now, the 3y, I know that we're right to differentiate that would become 3. And even though there's not a y there, I'm still going to have dy by dx because that 3 came about from differentiating something with respect to y when I said I was going to do it with respect to x. And then finally, the 6 here, we are just going to have 0. Now, from this, we can find an expression for dy by dx. Let me show you how. So if I decide now that I'm going to just keep anything that's got a dy by dx term in it on the left-hand side, but anything that doesn't, I'm going to move it over to the right-hand side, I would get something that looks like this. So 3y squared dy by dx plus 3 dy by dx is equal to, so taking the 1 over, minus 1, taking the 3x squared over, minus 3x squared. Lovely. Now, the reason that I've kept these little bits here is that I now have a common term in both, or a common factor, of dy by dx. I'm going to take that outside a set of brackets and I'm going to treat it as though it is an actual term now. So I get there 3y squared plus 3. So again, that's still equal to minus 1 minus 3x squared. You can probably see what I'm going to do now. So if I then just take my dy by dx and keep it there, where I'm sort of multiplying by this bracket here, and I'm taking that over, I'm going to divide by it. And there you have it. That's the question done. I now have differentiated this function that we had to start with that involved x's and y terms, but I've got an answer. Again, it involves x's and y's, but I've got it in the format that I like, with dy by dx equals, and we can use that then to find gradients, etc., all the way through. Thank you. Okay, so here's the second example, which is going to level up in 2 ways. The first is that if you have a look through, so you've got 4xy squared plus 6x squared over y is equal to 10. You'll notice that I now have a coupling, so I have the x and the y together in both of these terms. So the question also goes further this time because they're asking us to find the value of dy by dx, which is the same as asking for the gradient at the point 1, 1. So when we get to our final answer, we are going to be substituting in some values. If they wanted to take the question one step further, they could even start to ask you then for the equation of the tangent, because we've got our y1 and our x1 here. So we could put that into our formula, y minus y1 is equal to mx minus x1, or they could even ask you for the equation of the normal. And that would be sort of the next step in terms of if we had an exam style question. But let's just get started and see what we get to. So as we can see here, I've just rewritten it out slightly differently. This time I've rewritten the y from the denominator as a y to the power of minus 1, because many of you know I prefer to use the product rule than the quotient rule. It's just a bit easier to remember. So let's start by having a look at this first term here, 4xy squared. Now if I wanted to differentiate that with respect to x, it'd be great if I had just the 4x, but I don't. I've got that y involved there too. You have to sort of see this as two terms sort of being multiplied together, and so we're going to use the product rule for differentiation. So if I do it properly, I'll do it down the side here. So I'll say that u is 4x and v is y squared. So du by dx is obviously going to give me 4. dv by dy, I guess, but we should be differentiating with respect to x, so that's going to give me 2y, and then it's also going to leave me with that sort of dy by dx bit there, because I'm still differentiating with respect to x here. So if I put that back in, then I know that with the product rule, the u goes with the dv, the v goes with the du, and because it's an addition in the product rule, I don't really need to worry about which way round I put these. So I'll start with the 4x multiplied by 2y, dy by dx, plus, and then the 4y squared. Now that wasn't differentiated there, so we've got no dy dx's to worry about. When I have a look at the second term, oh the joy, they've given us another one, another sort of function where we've got those two parts being multiplied together. So I'll sort of do these in green now so you can see. So if I set u to be 6x squared, du by dx is going to give me 12x. I'm going to set v to be y to the power of minus 1. So dv by dx is going to be minus y, sorry, an equal sign. So minus y to the power of minus 2, and then dy by dx. So again, can add these, and this is why I kind of changed it to y to the power minus 1, because I prefer to use the product rule than the quotient rule. So we've got to add on 6x squared. Okay, that's a minus y there, so I'm actually just going to do this. So I've got a minus, and the y to the power of minus 2 there means I'm just going to write it at the bottom here. And then I've got a dy by dx there. And then again, the power of minus 1, I'm just going to write that at the bottom now. So plus 12x all over y. And again, when I differentiate this side, I'm going to get that that's equal to 0. Just sort of running out of space there. Okay, so let's start to tidy this up and put some bits together. So this section here, I'm going to get 8xy dy by dx. Here is quite straightforward, plus 4y squared. Okay, so here that's going to stay as it is, so minus 6x squared over y squared, dy by dx, if you want to put the little multiplier there, and then plus the 12x over y is equal to 0. So again, anything that involves a dy by dx, I'm going to sort of collect that together. So that's going to be this term with the dy by dx and this term with the dy by dx. Anything that hasn't, so this term and this term, I'm going to put those over to the right hand side. So I should have now 8xy minus 6x squared over y squared, and they have both got that dy by dx there, is equal to, so minus 12x over y minus 4y squared. Wonderful. So again, just popping the different bits over. dy by dx is equal to minus 12x over y minus 4y squared all over 8xy minus 6x squared over y squared. Now, usually at this point, we'd be starting to go through and to try and tidy this up so that we didn't have a sort of fraction in my numerator and a fraction in my denominator. However, the saving grace of this question, if we go back to the top, is that we are looking for it at the point 1, 1. So we know that we just need to know when x is 1 and when y is 1, what is the value of our gradient. So I can go back to this bit now. I don't need to worry too much about tidying up. I can just get the value of the gradient straight away. So the gradient, dy by dx, so it's going to be minus, so if I substitute in 1 there and 1 there, so minus 12. Substituting in 1 here, 1 squared, so take away 4, all over. So 8 times 1 times 1 is 8. 6 times by 1, all divided by 1, is going to give me a 6 there. So I'm going to get minus 16 over 2. So my gradient comes out as minus 8. And that is the answer to this question. I've found the value of dy by dx at that point there. Okay, and obviously just make sure you finish off by underlining your answer. As I said, they could extend it further by asking you to find the equation of the tangent. And if they were to do that, you've got enough information, so you'd have y minus y1 is equal to mx minus x1. So y minus 1, because we were told it was at the point 1, 1, is equal to minus 8x minus x1. So that's how they would level up the question in an exam. And we can see it's relatively straightforward in this example to do that. Okay, time for you to have a go.